Welcome to Lecture 13B. We'll be discussing the launch vehicle design. So, if you recall, you can develop a finite element model of each launch vehicle component, and the launch vehicle component uh, will then be assembled with other launch vehicle components to form a full vehicle model. This vehicle model usually will be coarse enough for dynamic analysis. This analysis will be sufficient to extract frequencies below 70 hertz, mode shapes and frequencies. And the idea then is to perform the coupled loads analysis, which is basically trying to determine how the spacecraft and the launch vehicle respond to each other when they're integrated together. Recall that the launch vehicle loads can be quite severe, and it could shake the spacecraft until it fails, or it could damage part of the launch vehicle. So we want to make sure that the launch vehicle components can survive the ascent environment from liftoff, ground winds, all that, all the way to when the spacecraft is basically deployed in its correct orbit. So this system level dynamic model plays a big role. Again, these models are not accurate to get stresses, but they tend to be very accurate for getting interface loads. And these interface loads can be very powerful in then driving a test program and also performing analyses that can help make sure they have sufficient structural margins. The couple load analysis produces maximum expected loads, axial and bending loads, torsion and shear loads. We covered this before, this is more of a reminder. And the driving load events for each of these components is found. It could be liftoff, atmospheric flight, max Q, for example, engine ignition and shutdowns, staging and separation events. So here is an example. I have this component here drawn with an outline in black. And you can see here the couple of those analysis produces this axial loading, compression axial load, which is predicted by the dynamic analysis. For this particular component, we can get the axial load, the bending load, the shear load, and even torsion load. That's the output, is to be able to get uh, loads at different locations within the structure. And so it depends where you get the output, for example. But these are the loads I'm going to use now to basically make sure that I have sufficient structural margins and that I have a good test program, really intended to ensure that the structure is robust through the life of the program. And so, how do I go about that? I'm going to take these loads. I could have hundreds of loads, but I need to come up with a smart way of testing it. So, you may want to come and trying to figure out what are the right loads I need for the design. And so here you have the qualification testing. This qualification test needs to be modeled, and you want to model this before you actually test to make sure you can come up with the right loads that you need in this test. Now, you can't test you could test hundreds of combination, but that might be inefficient. The right thing to do is to figure out, hey, what are the load cases I can apply that could envelope other load cases? And the idea then is to come up with an understanding of the loading environments that I need for this testing. You also want to make sure that you uh, create a finite element model that's actually quite uh, fine, good fine mesh for the flight configuration. So not just for the test configuration, for the flight configuration as well, because you're going to have some flight load cases that you may want to make sure that you then compare against the test configuration. The test configuration, I apologize for that. The test configuration needs to really envelope the margins in this test need to be less than the margins in flight. In other words, I want to make sure that every critical failure mode of this structure is exercised in a little bit harsher than in flight, because that's how I can demonstrate that this test is actually doing is exercising those failure modes accurately. Secondly, there will be differences between flight and, and test configuration. So you may want to make sure that for every critical failure mode, we are exercising the critical failure modes. And so that may mean that the qualification test may need to be adjusted in a way so that ultimate test loads are adjusted in such a way that you're covering all the bases. So this final model and these qualification tests need to be compared. You want to make sure you have good model correlation and to ensure that the model matches the test. And that means the strains, the deflections, because the strains and deflection tell you a lot about the load path. Am I getting the right load paths in the structure finite element model? Another thing that's important here is that you want to make sure that the test is actually doing the right thing. So are the actuator loads applied into the structure correctly? So that's what the finite model could show you that. Because for example, if I were to apply actuator loads and then the strains in the structure somehow are lower than in the finite element configuration, you may start thinking, well, maybe perhaps I'm not applying the loads correctly into the structure. Sorry about that. So you want to make sure, and there's many cases where one thinks that the actuator loads are putting loads into a structure, but it's actually not. And that's where this correlation becomes important. So the finite element model plays a crucial role in ensuring that you are doing the right test, that and it also serves as a transfer function between flight and the test configuration. That's why this correlation is so essential. And also, this analysis is going to help you to identify the critical failure modes of the structure. Could be buckling, could be stress over here, for example, in the stress concentration. It could be many different things. And that's why it's so important to ensure that this finite model matches as best as possible to the test configuration. And then, after you get that right, you may want to then make sure that we have the right test like you fly differences. So you're going to have boundary conditions from the test stand that are not present in flight. You're going to have environments that may not be present in the test compared to flight. As an example, if you have a composite structure that's tested at ambient conditions, but in the flight configuration, the composite is going to see, say, 300 degrees F. Well, the strength in flight for the composite is likely going to be lower. Well, at room temperature is going to be whatever it is. And so say that there's a degradation in strength of the composite of 20% between the test configuration and temperature and the flight configuration. Because composites will you typically see a strength reduction. So there's a 20% strength reduction. You may want to take the qualification loads and increase them by a factor of another 20% to account for that difference that in the fact that this test configuration is not fully flight-like. Another example would be missing loads. You could have loads that are occurring in flight that I did not consider in the test, but you have to account for them somehow. So what you could do is increase the loads, the other loads, and ensure that the structural margins in the areas of criticality envelope the margins in flight. So again, these adjustment factors can be very helpful in incorporating any test like a flight differences. Once you have these test like a flight differences and the factors calculated for each of these things, which again is important to really quantify it, and that's why you need the finite element model for the test configuration and the finite element model for the flight configuration. Once you have that, you can take the ultimate test load, you can divide that by the factor of safety, and then you can divide it by all these adjustment factors, and that will give you the maximum allowable limit load, the limit load that you can actually survive. And so this limit load then is entered into the finite element model to calculate margins. And you want to make sure that the margins for every critical failure mode is greater than zero, perhaps 10%, greater than 10% to ensure that we can cover for issues like non-conformances later in the production program, during the production phase. And so, yeah, so that's how you go about this. That's the overall structural assessment. Again, you have a limit load that came from the couple loads analysis. You will then perform qualification testing to limit loads, and the limit loads will be increased by the factor of safety 1.25 maybe if it's a unmanned vehicle, 1.4 if it's a human space flight, like for NASA, and you will increase that, and then you will increase it further to account for these adjustment factors. So you want to run that test fairly at high loads, and so the idea then is you test it to those levels, and then you can then use the limit loads to calculate the structural margins for every single failure mode of concern. And the overall structural assessment process then will account for the environmental degradation, the boundary condition differences between test and flight, and the absence of loads are actually present in reality. So, so let's go back and kind of discuss some of these things in more detail. So you have this bending load, this axial load, this shear load, and hopefully your test stand is able to introduce these loads. And if it's not, you may want to find a way of enveloping with the whatever loads you can apply, enveloping every critical failure mode between test and flight. You want your test to be worse than in flight because you're testing. So you want to make sure the conditions in the test configuration are worse and envelope in flight. Typically, you will test a dedicated qualification test article. I'll be talking about pro qualification later, where you actually test and then you fly the same unit. But assume for a second that you will do a dedicated qualification test article. Typically, these dedicated qualification test articles are fabricated. This qualification article is fabricated specifically for the test, and it will be a flight design. It's going to be the same, using the same drawings, the same processes, the same manufacturing. That's really what you want in your design. You don't want to be um, using a process that was not used in the manufacturing. Otherwise, there could be significant issues in what you're doing. Once you've come up with the test loads, and the static test loads again are derived from maximum expected loads, the 99 loads that we discussed. You apply the shear bending loads from the couple loads analyses, and you may have to apply even pressure if it's a pressurized tank. And the idea is to adjust to account for the flight to test differences, boundary conditions, temperatures, and then your ultimate loads become the test factor of safety times the adjusted loads. And these numbers are going to be greater than one over here. The boundary condition factor, the environmental factor, the missing loads. So these ultimate loads could be quite high actually, greater than 1.25 after you adjust for all the differences that you have. And then you want to instrument the test article with with a lot of care. You want to provide enough data. You want to be able to get enough data from the test. They can then do an analysis correlation against a finite element model. You can use it then to assess, for example, yielding, permanent deformation. You can also make sure that you're properly applying the loads into the structure. So the strain and deflection gauges play a big role. The correlation can be quite affected if you're not careful. You want to assess the adequacy of the finite element model by comparing the analysis and test responses, and the compliance on the test stand could be quite significant. You want to improve the model to resolve any differences with test, and that means trying to rectify any issues with the model that could be causing it to be incorrect. Now there could be a situation where the model is correct and perhaps the test configuration, you're doing something incorrectly there that could be causing an issue. And so the design assessment with an uncorrelated model will be really quite suspect. If I use this finite model for the flight configuration to calculate structural margins, and this finite element model was incorrect, then you're really writing margins with a wrong model, and that could be a problem. You want to assess whether critical failure modes were really fully tested, and that's why you want a good finite element model. Now, there could be differences between the test and configuration and the finite element model of the test configuration, and those differences are going to be sometimes driven by the fact that strain gauges could be off in the positioning. You could be looking at a hoop strain gauge that was installed on the test stand configuration, on the test configuration, but then in the model, it could be an actual strain gauge. So you could have incorrect application strain gauges compared to drawings. If you put strain gauges near areas of high strain gradients, that can also be a problem because then your final model will be off, because it will be very hard to get it right if you have strains near strain gradients. So putting strain gauges in areas where the strain is not changing very much is useful, but it's also worth putting strain gauges in areas of gradients. That's okay. Bottom line, there could be a number of issues for why your strain gauges are not matching the test. Channels could be off. So you may think you're looking at a particular channel, but you're actually looking at a different strain gauge. And then maybe there's a strain gauge sensitivity where the strain ratings are fairly low, and so you tend to be more off when strains are fairly low. But if strains are off, it may be worth looking at what's going on. Perhaps the load is not applied in a way that's appropriate. You want to use a finite element to then assess the design of each of the components. You want to consider the most critical load combination, quantify the influence of hardware variability, and that means dispersions in geometry, dispersions in material properties. All that, it becomes quite important to ensure that we're doing the right thing. And then you can determine the stresses and strains out of here, and then you can assess the structural margins for each of the failure modes of concern. So again, you apply the highest limit loads from the couple loads analyses, and then predict the stress at limit load. Then you use that information here, along with the factor of safety, and then you have the allowable strength, which has been adjusted for the environments, and hopefully is the A base is allowable if it's a primary structure. That will give you a margin of safety. And recall that the factor of safety protects you against uncertainties. The limit stress is usually the highest loads that you can expect, but that's actually statistically derived. And then the strength is also statistically derived and is based on coupon testing or subcomponent level testing as well. So you can then, per the requirements, and we'll talk about requirements later, assess strength and fatigue and buckling. Once you have the predicted stress at limit load, you will then plug it in here. And visually, let's look at what's going on. So the stress could be non-linearly behaving against load application. At limit load, you will calculate the limit stress. We talked about that already, but I'm showing you this graphically. The strength of the structure could be over here. So that's your A basis strength. The strength divided by the factor of safety is this ratio here, strength divided by factor of safety. And so what you want to make sure is that the strength divided by factor of safety, that there's space between that dashed line that's red and this black line that's dashed. And so this is your margin of safety here. We want to make sure that that margin of safety is greater than zero and perhaps even 10% to keep some pocket margin. Again, very, very important application that we're talking about, right? So the loads that they'll launch must be less than the qualified limit loads. So anytime you launch a vehicle, you want to make sure you're within the qualified limit loads. You may have to apply reduced load levels that they'll launch because maybe there's hardware discrepancies like impact damage, composite defects. And the way you can determine whether the loads are within the qualified limit loads is sometimes you have to send weather balloons to make sure that you're staying within the qualified capability. Day of launch loads are monitored to ensure that these are within the acceptable structural limits. Typically, we're checking the pressure in the COPVs, pressure in propellant tanks, temperature driving minimum structural margins. Um, Sometimes you have to look at the vehicle station loads, and also you want to look at temperatures driving minimum structural margins. So we want to make sure that all the parameters are within the qualified limits of the system. The structural assessment process is very important that it follows a building block approach. What is really the building block approach? The building block approach provides you an approach to reducing the number of failures late in the program. So if I have a number of specimens I can test, and I can create models to correlate the models to the failure modes I get in a smaller coupon configuration, that's very advantageous because when I go to the next level sub-element test, there's a sub-element test. And in this case, what you see here is a bolted joint in a composite structure. This configuration is going to have failure modes that are quite complex, like fiber failure, matrix cracking, and things like that, delamination, and so forth. If I'm able to develop a model that's able to correlate the next level up, and then I can use a model to then predict the failure of more complicated tests above, for example, this one here, or then even the te- actually predicting the failure of a test article, that'll be very valuable because then you can take that test that you did at the sub element level test and you can use a model to further refine and optimize the design. But if you don't do that and you skip all these steps and you go straight and you use a model that's not very well validated and you step into this test, it's very possible that that test will fail. And if it fails too early below the requirements set by the program, then in that case, you're going to have to redesign, which means you have wasted time and there are significant delays to cost to the schedule and significant cost associated with this. So it's very important to start at the coupon level, really get the characteristics of the material, fully characterize the material in all the ways. The properties need to be defined. You want to get the strength, the failure, the potential failure modes, and things like that. And using that test you can then further improve the models, and then that's going to help you increase success as you move to the full scale um, level. So as you can see, testing is equally important to analysis. They complement each other. The analysis is providing you the opportunities to optimize the design, but it's also giving you the opportunity to make sure that your full scale test, which will have cost probably millions, that test is actually ultimately successful. And if you don't have that model, you're really going into a test without knowing what will happen. Another thing that this type of testing is doing from the bottoms up is really helping you increase success in terms of determining whether the manufacturing processes you have implemented in the test program are adequate. And that's very valuable in this kind of uh, uh, in this kind of world where you're really looking at having the best success. And so if your manufacturing processes are qualified all the way from the bottom up, then you are gaining confidence. For example, say that when I'm manufacturing these coupons and I'm using the cure cycle for these coupons, and the cure cycle happens to somehow cause dry plies or causes too much resin, whatever that might be, you will know quickly what's going on, and you can rectify the cure cycle to get a better product. But the idea then is to really go from the bottoms up and increase your confidence as you go all the way to the full scale approach, the full scale test I meant. So, in the qualification process, in the building block approach, what we're looking for is making sure that we have good controls over material specifications and over process qualifications. And that means supplier qualification, fiber requirements, pre-preg requirements. You want to make sure that we have good pre-preg requirements, and that can involve fiber volume fraction being in within a control, within a spec, resin chemistry, the mechanical properties such as modulus and things like that. You want to make sure that the forms, whether it's tape or fabric, they're really good. Um, and then you have the cure cycle, quality controls, and manufacturing characteristics. So all this is very important when you're uh, really defining these material specifications. And you want those material specifications to be fairly constant uh, in the life of the program. During the development process, it's okay to modify some of these to really increase the confidence. And these numbers will further mature as the program matures. Incoming and receiving tests is very important. As you receive fibers, for example, you can check that the properties of the fibers is as you expected. Process specifications is extremely important. Process specifications include storage and handling, the cure cycle, how you lay up and bag the materials, the in-process quality controls I talked about earlier, which is like tagging tests and witness panel test, post-processing quality control, such as inspections, and then you have acceptable anomalies and splicing. So these process specifications also need to be set as you move forward. Any changes to any of these things can cause a reduction in strength, and you perhaps don't want to perform a full qualification testing to demonstrate that you're okay. But in fact, what you want to really do is ensure that you have the highest confidence as the program matures. So here's the building block approach from the aircraft perspective, but I'm borrowing it here because I think it's quite applicable and applies to launch vehicles as well and spacecraft. You have your coupons here, which could be in the thousands, because those are the coupons you're really testing to get the A basis and the B basis strength that you need for your design. And then you go again to the element testing, and that's more in the hundreds. And then you go to the sub element or larger panel subcomponent level test. This is in the dozens. So coupon and elements, that's going to consider mechanical properties. That's where you'll get them from the coupon testing. Interlaminar properties, stress concentrations, and durability, bolted joints. So now you're going into the bolted joints. So this coupon testing can also help you really gain confidence in the stress concentrations. The bolted joints will be a level up, and that's going to give you confidence in the strength of a bolted joint. But it could be bonded joint as well. Impact damage characterization. Now you can start looking at what will happen if I drop a tool, and you want to really characterize all the damage threats as we had discussed earlier, and you want to make sure that you have a full set of confidence in all the damage threats and that you've tested those damage threats, because that's going to help you come up with a allowable that's going to cover impact damage events. And so then you can use the allowable to then go to the next level for the large panel test, ensure that you're robust to the requirements that have been set forth, that your models are matching the test, that the strain gauging and the deformations and the deflections, that all that between the models and the test, we have good confidence. So again, this impact damage characterization is extremely important. And then the environmental factors can include thermal and it can include moisture. And these factors are of extreme importance because they're going to decrease the strength of a composite, for example. And so you want to make sure that when you do the test, that you're really characterizing those environments as well. And so that's why you want to make sure that the strength properties fully account for the effects of temperature and moisture. And as you move up to the large panel test, you can then test few samples to see if your assumptions on how the failure modes, whether the failure modes were consistent, because moisture and temperature can also shift the failure mode, for example, from matrix cracking to maybe say bearing failure or net section failure. Whatever it is, these environmental factors can really shift how things change. And then I can move up to components now. These are larger scale components, and I'm looking at now testing a wing, for example. And in this case, we want to make sure that I'm validating. Here, I should have validated some amount, but you want to validate the design concepts, verify analysis methods, provide substantiating data for the material design values. And so that means, okay, did my model predict very well based on the material design values I had selected? You want to demonstrate compliance with criteria, demonstrate the ability of the finite element models to predict the strains. And so this is what you're doing through this test. And again, why I need the analysis to match the test. We need to understand that because you may say, well, the test is just enough. But the reason you want to make sure that the test is doing the analysis is doing a good job is because the analysis is your transfer function between the flight testing, sorry, the testing on the ground versus the flight condition. Remember, the boundary conditions are different. The way you're going to load up the wing or the way you're going to load up this fuselage is, or the aircraft or the launch vehicle is going to be fundamentally different from flight. You can make it similar, but they're going to be different. And that's why your analysis here and making sure it matches test is of ultimate importance because that gives you that transfer function between ground testing and flight. And further, the analysis is going to make sure that you're testing every critical failure mode that could be of importance. Thermal and moisture strains should be accounted for in the finite element model for each of the critical conditions of concern. Again, we want to make sure that as we go up from the coupon level testing to the full scale test, that we're gaining confidence in the modeling, that we're gaining confidence in the allowables, that we're gaining confidence that we've covered all the durability aspects, all the impact damage characterization aspects. So when I step into this full scale uh, launch vehicle aircraft test, that I have the ultimate confidence it will succeed. And that test it will be successful. But if a failure were to happen, let's presume and we covered a few examples with Boeing aircraft that failed late in the game. Well, that is not bad either. We don't want that to happen because that will be costly in terms of schedule and also uh, delays. But it is okay if we have a failure late in the game because failure late in the game, that's good. It showed you the value of the test itself. Perhaps you missed something earlier in the process. Perhaps manufacturing large scale structure was fundamentally different from testing a smaller scale structure. And so the full scale test did what it's supposed to do, which is to surface any weaknesses in the design. And so if it failed, then that is good because we don't want that failure to have happened in flight. So that also shows the value of the test itself. But you don't want the failure, but if it happened, you take it and you learn from it. That's where I want the failure. I want the failure there. I don't want the failure when I have astronauts or passengers in there or an expensive payload. I'd rather have that failure when it doesn't really matter as much in terms of impact. Uh, it will have an impact, however, to the cost and schedule. So if I look at a fail-safe design, and that's one of the aspects that is important to understand. The section 5.3.2.4 of the AISS 110, which governs the launch vehicle spacecraft designs in general, provides a provision for the use of the B basis allowable. And B basis allowable is really used in situations where you have a fail-safe design. And so what do I mean with fail-safe design? It's a design that if say you have five trusses that's holding a weight, if one of the trusses failed and the other four trusses can take the load, call that a fail-safe design because the design is able to take the load when something else fails. And so I can then, if I'm able to design for fail-safe, you can use a B basis allowable as a minimum. What a fail-safe is not the same thing as a safe life. And the safe life in the launch vehicle arena versus safe life in aircraft arena also means very differently. Here I'm covering safe life as it covers for launch vehicles. Safe life is really a damage tolerance design where a flaw is assumed in the structure and the structure is shown to be good for whatever the surface life is times four. So that's what you're evaluating there for safe life. Well, fail safe is not the same thing because fail safe is making sure that if a bolt was missing, say, the structure can still carry the additional load through the other bolts. That's what a fail-safe design is. And So that is actually very valuable if you can incorporate with very limited weight increase in penalty. If you're able to impact your design by incorporating a fail-safe feature, go ahead and do that because that's going to increase your confidence and it may decrease the amount of work you need to do for the verification of the structure as well. So there's a lot of value in really looking at implementing fail-safe designs while also limiting the impacts on weight. Very important considerations. Now, another thing in this building block approach that needs to be considered over here, that building block approach and this building block approach, both of them are different looking, but they are really driving to the same point, is that you want your allowables to really encompass all the potential damages that you could have. So, for example, let's have a pristine material, the strength will be all the way up here. And then when I have processing anomalies, say I have surface irregularities, splicing, waviness in the composite, inclusions and voids, I want my allowable to be able to take account for that. And you can see here that these processing anomalies will further bring the strength down to some percentage. And then you then want to look at perhaps damage that could be visible. For example, somebody drops a tool, but you cannot see it. That'll be a non-visible damage. Now somebody drops a little bit heavier tool. Well, in that scenario, that could you could probably see the damage, and that could be a problem. So that is going to cause a significant reduction in strength potentially. Then you have your design environment, and your design environment can also, such as thermal and moisture, can further reduce your allowable. So accounting for all this will protect the composite during the life of the program for all various processing anomalies and damage. And if your allowable can account for that, when you encounter them in real life, then you don't have to worry about it as much because you accounted for it. Now, if you don't account for it, that's still okay. That just means that you have to do more work when something happens. That could include having to do a repair later on, or you may have to cut out the area of damage. What you do definitely want to protect is against non-visible damage. That is going to be painful because if somebody drops a tool and it's not visible, but there's a lot of damage behind the scenes, then that could be a problem. And it could be a problem during the flight conditions. You could have a catastrophic event. So we don't want that. We want to design structures so that you account for all the damage. And if you don't account for the damage or portion of the damage, you have mitigating factors that can be implemented later in the design process. In the production phase, is what I meant. In the production phase, you want to have ways to capture that if you can. What I'm going to cover now has been adapted from a presentation I gave at the American Society of Composites in 2016. And I think it's useful to look at what we're covering there because we're covering a number of things there that really relate to what we're trying to hit on today on the launch vehicle or spacecraft designs. I want to remind you that the process for certifying spacecraft structures can be very lengthy. And it really starts with the opportunity, the announcement of opportunity to release, and then it continues on in the early concept here to authority to proceed. And then you step into the preliminary design review, the critical design review, the system integration review, and then the launch anomaly support. That's kind of like the process that you follow. And so you definitely want to put a lot of effort early in the program so that late in the program you can be successful. If you cut a lot of steps here, you may go into here and then you may not even meet the requirements, or there could be a miscommunication. Things are not really working well. There may be a lot of anomalies late in the game. Regardless, that is one approach. That is one approach, and it's not the only approach. Another approach is to just go straight and start manufacturing, start learning right away, which has a lot of cost, up from cost, and you're gonna perhaps have a lot of failures early on. But when something succeeds, you know it works, and you just go for it. And then you try to figure out how my design verification should show that hey, that should be okay. So two approaches. The approach that guarantees usually that success is starting from the bottom up. Building block approach, going through reviews and really understanding how everything fits together because a launch vehicle and spacecraft design are quite complex. One of the goals that should be in your minds as you work through your projects is you want to achieve and you want to try to succeed to 100% mission success. That means making sure the aircraft is delivering passengers, that the mission's objectives are being met. And that means sometimes identifying issues early in the design program, identifying issues affecting the space hardware, assessing the risk of flight hardware as well, even during testing. But that is challenging. And, as I showed you earlier, the factors of safety can be even as low as 10%, 25% for qualified structure, 2.0 when you're not qualifying the structure through testing. And so the low factors of safety means they're really driven by weight savings, but also means you have razor thin margins. Not quite 100% because you're designing to A basis, so that protects against statistical variations, but it also protects us against the loads that are 9990, the limit loads that we talked about. So you have that as well. The low production rate motivates making sure a lot of times you have low production rates. Aircraft applications have a high production rate, but that motivates really finding the root cause to a lot of these failure, anomalies that you may have. Designs and failure modes can be quite complex. Designs are subject to severe launch ascent loads, uh, particularly the failure modes in composite structures can be complex. Bonded joints as well. And designs really are subject to very severe launch and ascent loads. So you want to make sure your structure can survive through all the phases of flight and that it maintains that integrity as you go through. But to achieve that, it really requires a lot of other things, ensuring that you have an effective communication between the design authority, the oversight organization, and to ensure that you have the customer goals in mind as you're trying to achieve that. So we ought to use a building block approach when you can to characterize the properties and build that confidence in analysis via testing. That confidence is extremely important to really achieve because if you don't do that, you're going to have late failures that will be a problem. We want to evaluate the baseline design, and that means evaluating the structural design, structural qualification test. You also want to verify the evaluating the baseline design also means making sure they've performed a structural design verification and validation, and they're managing uncertainty and quantification risk. So that means they're going to have uncertainty in certain material properties, uncertainty in certain loads or something like that. And so you can then use the analysis has been anchored to study the sensitivity to those uncertainties. And that's going to help you further quantify the risk of a problem, which may not be a problem. You may not have a problem at all. But that's why you do the analysis and the test, and you do the sensitivity studies. Okay. So you want to evaluate the as-built hardware to identify mission-critical issues and implement a robust workmanship verification. And that what that means is that you went through a design verification phase, but you want to make sure that the hardware as you built it is good to go. And to do that, we already covered some of aspects of that, but we want to make sure that the as-built hardware has has been properly verified through workmanship. That means doing a proof test, doing the NDE, or something like that. Apply lessons learned from past and failure and past. You want to apply lessons learned from past failures and anomalies. So you want to keep a database of the things that have gone wrong, because that's really going to help you moving forward. It's going to help you really understand whether we have a problem with later on. If you have a failure, you can say, okay, no, I checked my database. We didn't repeat that mistake again. But it really sucks if you repeat that mistake again. You don't want to do that if you can help it. I want to cover an area that's very important, and this basically serves as outline to this particular portion of the briefing. we're not talking about communication, so I'll be touching on communication now. Communication really builds understanding up front, really getting those requirements very clear, complete, and really setting the expectations for the milestones that need to be followed to make sure that we're clear about the expectations relative to the design, the mission objectives. That's very important. And you want to integrate all the different organizations early in the process to make sure we are applying the best practices relative to the test analysis and workmanship of structures. Also, right, nowadays conducting face-to-face meetings may not be possible, but it really helps building that relationship and ensuring that we have a good working relationship. A lot of the problems that get solved get flushed out when you have those relationships. And so those professional relationships help you really find synergy in the certification process. And so that's why you want to make sure that you know there's chemistry that's getting developed because that usually leads to success. Now, the bottom line is that that is not a necessary ingredient. It is a helpful ingredient, but it's not the only thing that's going to make it successful. What really makes it successful is to have the expectations clear, with the requirements clear, with everything that goes to go, all the mission objectives clear, for example. If you can keep that straight, then you could achieve success. And you want to do uh, spot checks during the process, during the development process, to make sure things are going in line as expectations. Now there are requirements that are imposed by the FAA and also the launch vehicles and spacecraft. And while they are their gold standard, you cannot always achieve them perfectly. And so that's why tailoring is usually submitted and evaluated. So you want to look at creative alternate options in those cases to try to achieve the same intent of those requirements. An optimal collaborative environment facilitates communication, data transmittals, resolution of concerns, and promotes the identification of technical issues. So here what you see is that the BBA can decrease the likelihood of costly failures by surfacing issues early in the design process. And so I already covered that, but the point here is that while the building block approach in the testing side does increase that likelihood of success, so does analysis. And so, due to cost constraints and schedule pressure, sometimes you will see that the elements of the building block approach are fully ignored. And so, what is the risk of not following the building block approach? What are the issues you may encounter? You're going to see different material properties are discovered late in the design process. What's that going to do for you? It's going to cause you to have to even redesign possibly. Mitigation is usually achieved if you don't want to have that whole building block approach to characterize the material properties. You may want to carry an additional uncertainty factor during the design process. Failure modes, and as an example, let me give you an example. Say you don't have a perfect A basis for the materials in question. Well, with the limited set of testing you have, just make sure that you're carrying an additional factor that covers for the lack of the full test and the full coupon level testing, because that way, um, later on, if you have to do more testing and your A basis allowable drops, you covered for that. That's an example. It doesn't mean it has happened before, but it's an example so you have a clear understanding what we're talking about. And so moving forward here, what we want to do then is to continue building an understanding of the failure modes, and they could have been missed until the full scale testing. The mitigation is really to perform testing early in the design process. So I kind of covered that already, but I'm just bringing that in the context of not following the BBA, the building block approach. Models are not test validated. If the models are not test validated, then you may have discrepant hardware that may be difficult to analyze and may require extensive testing or necessary repairs. Okay. And so And so what we want to do is ensure that if the models are not test validated, that you understand that it may be very difficult to really evaluate those discrepant hardware. And so that's going to require maybe extensive testing later on or necessary repairs. So just keep that in mind as you're working through models and ensuring that they do get validated if you can. Dispersions are not well quantified. So that if the dispersions are not well quantified either on the loads or characterization side of the material, then you could be potentially facing a proof test failure or flight failure. So applying uncertainty factors or using historical dispersion data could achieve help here. It could reduce the risk. So examples of where the building block approach has really not uh, cutting corners on the building block approach has caused issues. That entails, for example, if you characterize the mechanical properties at the operating environment and you only test it at particular temperatures, but not over the whole critical range, the incomplete material characterization can lead to incorrect assessments. So, in one occasion, we saw structural margins changing over 20% when the complete data set was collected. As a consequence, what that led was to a catastrophic failure event. So, or an anomaly. And so, the lesson learned there is hey, I should characterize the materials over the critical range. And I should be careful about the assumptions I'm making when I interpolate or extrapolate because not doing a full battery of tests can have big implications. Now, you also don't want to go overkill and test every single temperature, but if the temperature range looks fairly large, you may want to consider it. Also, in some cases, testing over the full range could also, while it may seem expensive initially, could actually later on lead to a greater reduction in weight. For example, if the strength in between temperatures for whatever reason was higher, I could take advantage of that. Um, another example is the evaluation of a composite bolted joint under complex loading conditions. An adequate test program will typically characterize the fundamental mechanical and strength properties of lamina, such as open or field hold composite test. Anchoring an analytical model to test can be quite important and further validating analytical models with more complex tests, such as single-sided and double-sided bearing bypass tests, can be very important. In one case, design issues would have been caught really early on if the bolted joint testing had been done early in the design program and the analysis was validated. But if that was not addressed, then that will have surfaced later on in the full-scale test, which is what happened. And so that cost was costly and caused delays. That's an example. So that's why it's good to test early on and learn. Now you have the structural design verification and validation. We talked about that here in this little outline I had here. You want to do a verification, structural design verification and validation. That's very important because you're gonna make mistakes. Not everybody is perfect. So typical errors that are caused are failure modes evaluated inadequately. That can be a problem. So say a very important failure mode is fiber failure, but all you did was to evaluate some other failure mode like delamination, and you didn't pay attention to that failure mode. That could be a typical error. Incorrect representation of composites, putting the wrong ply angles or the wrong thickness can be a problem. Mass definitions are incorrect. That's going to change the frequencies, and it's going to change the dynamic characterization of the structure. Incorrect geometry compared to the CAD model, that can be a problem. And I'll give examples of that. Incorrect characterization of the stiffness for the joints, that can be a problem as well. All that is going to drive errors in the modeling that could change the character of the structural response. Typical modeling checks that should be done. You want to compare the model against the CAD model. You want to compare the composite ply definition with drawings and the manufacturing. And particularly, you want to make sure the drawing matches the manufacturing too, because you could have the composite matching the drawing, but the drawing is not, the manufacturing is not matching the drawing, which could be a problem. Compare material properties in the model to material data. Compare mass properties in the model to data. All that is important. Evaluate adequacy of the interface connections and boundary conditions. You want to perform checks that the model is well connected because otherwise you could have cracks that are not supposed to be there, and that could be an issue. Check that the model is well grounded and that you have the proper mechanisms in place, such as the boundary conditions are correct. The surface normals could be incorrect, which means the composite stack up could be incorrect. So you want to check that. Probably not an issue if you have isotropic materials. A 1G check, which means take the model and apply a gravity load. That's very helpful to check that your units for weight are correct or that nothing is disconnected incorrectly. And you want to exaggerate the deformation dramatically to make sure that everything looks like it's supposed to. You want to do checks on the elements to make sure that the finite elements that you're using are really good, and you want to make sure that so it is important to make sure that the element quality checks are done. The 1D implementation is also very important to make sure you're using the right um, centroid, the offsets, the shear center, that you're using the right element for the right application. If it's a beam, it looks like a beam, use a beam. If it's a shell, use a shell. But if it's a solid, don't try to model as a beam. You also want to assess simplifications of the hardware omissions. So, for example, if you don't put a cutout or a secondary structure or propulsion line, just make sure that's a good assumption. You also want to make a lot of rigid body checks when you can. The trends that we're seeing more and more is that there's large models being used that have insufficient checks. The margin evaluation are basically using very coarse meshes near areas of stress concentration. And so, say you have a hole in a structure, and you only have 4 or 5 elements around the hole. Well, that is not a good mesh density to properly capture the stress concentration. As a consequence, it's very important to make sure that a hand calculation is done in those situations because it will be more accurate than actually trusting the finite element model. So it's very important then to ensure your margin evaluation is done with the highest confidence approach. And it doesn't have to be the finite element model. Large models are being developed, but you want to make sure that if you develop a large model, that you put the fine mesh in areas where it's needed and coarse mesh in areas where it doesn't matter. A lack of sufficient engineering judgment is being applied at negative or positive margin locations. Sometimes the artifacts are caused by a modeling issue. Sorry about that. And so you want to make sure that all the negative margins are assessed very carefully to make sure it's not just a margin, is a artifact. Here are some examples of errors. Say that the drawing has this material like this, but you model it like that. That's going to cause the stiffness of the panel to change. If you model the cutout here versus here, that's going to change the model characteristics. If you have the brackets, you have this panel and this panel, and there are um, then you want to make sure that these clips are properly modeled. Say you have this as a drawing, and you can see here clearly that this looks more like a shell. Well, if this was modeled as a beam, that's incorrect. You can see here at the top, um, it looks very different, but it was modeled as rigid. You probably want to use shells or solid elements. So you can see here there's a big difference between how you model something, how you represent and simplify a drawing into an accurate physical representation. Here on the right hand side, you see a drawing again. And this looks like a solid extension. So this was modeled as a beam. Well, that's incorrect, should be modeled as a solid. Here you have a tube. That should be modeled as a thin shell, so that's fine. Here at the bottom is a solid base. Modeling that as a shell is incorrect because that's not how a solid can be represented. So here you model that as a solid element. Making sure that you're putting the appropriate representation for what's in the drawing is of ultimate importance. Here you have a typical beam that's attached to a plate. You want to make sure that that beam is attached to a plate properly, and you want to make sure that the footprint is correctly attaching to that backbone here. Here you also have a stiffener on a skin. Here, that's one way to model it, where you have a rigid bar connected to this skin. However, that's going to produce incorrect results because you're going to have extra rotation. The more appropriate approach is to connect the whole footprint because that's how it looks like in real life. One approach to really model and come up with simplifications to a model is to do a subscale model of a joint. So if you have a subscale model, you can then represent that joint in a by coming up with a spring stiffness that gives you the same response as this structure. So again, very important to figure out ways of modeling structures in a way that's smart, efficient, but gives you the same answers. And so modeling this bracket, every single location on a spacecraft will be too computationally expensive. But if you can create subscale models to understand the stiffening, the spring stiffness that you need to get the same response, then you can now take these million degrees of freedom. It's not millions, probably 100,000, and then just replace that with a spring. That'll give you the same response. So again, modeling is very important. How you model things is very important, and how you simplify models is very important. Sensitivity studies can be added, can be of added value when comparing just calculating structural margin. If you just calculate structural margin with nominal properties, it gives you very little information about what is going on. But when you actually do a, a, a margin calculation, but you study what parameters affect the margin, like modulus, thickness, what things matter, I think in those points in time, you learn more about how the structure responds. So sensitivity studies can be very valuable, especially if you shell elements and you can quickly change thickness, you can quickly change modulus. Those can be very valuable shell elements or beam elements. The risk of flight failure can be validated using probabilistic approach if the margin is negative, but you have to really have a good characterization of the part-to-part variations, the material variations like CTE, Poisson ratio. You can ensure the failure modes are well understood from component level testing before you do a probabilistic approach, and then you can calculate the probability of failure. But you need to have a good understanding of the failure mode. You have to have a good understanding how the properties vary, like the thickness of the different parts, the material variations of the different parts, having the correct distribution of the loads and having a correct distribution of the strength, all that matter. And then using all that information, you can then come up with a probabilistic calculation. I really want to talk about how important it is to understand that this is a design verification that we're talking about, all this, even the testing, all that, the building block approach, all that. But we also need to make sure that the hardware has been correctly built. And acceptance of the baseline design does not mean, verifying the design does not mean that the flight unit is good to go. You have to verify for workmanship issues, manufacturing deviations are bound to occur. Hardware issues are identified at specialized on-site reviews. And you can do a specialized on-site review through something called the pedigree process. In pedigree review process, there's a paper written by Dr. Wayne Goodman, which you can find online, and that paper goes through that. But the top level view here is that you need to provide engineering justification for any test like you fly exceptions. If you have anything that is not like flight, you have to provide justification. And there's this aerospace store that I recommend you read. You can pause the video, download it now, and read it. And it's going to talk about uh, how to ensure that testing is like um, flight like. Qualification approach. A lot of times when a rocket evolves or aircraft evolves, you're gonna have some components that have undergone some amount of modification for weight savings, cost savings, or improvements based on issues in the past that occurred in the past. So it's important to then make sure you have a good qualification approach for those components that are have gone a change. Manufacturing documentation of single point failure, making sure that you have a good understanding of the manufacturing of any location that has single point failure, making sure you have strong rationale for any hardware that's getting repaired or accepted. So say, for example, you have a thickness that's too low that does not meet the drawings. Well, you want to make sure that you have a good understanding of an engineering disposition and rationale for why you're using the hardware as is or why you're repairing it. And so if you're going to use it as is, you want to have experimental evidence that for why, do I have good rationale for just using it as is? And that can involve using additional qualification testing or analysis or a combination. Corrective actions are then used to prevent hardware anomalies from future flights. You want to make sure you implemented any corrective actions that are associated with um, any anomalies that were found in the past that you're doing something about it, and they have shown that mitigation does work. Assessment of escapes and their likely impact on mission performance, out of family results identified through statistical process controls, and you want to make sure that any out of family results are, you're trying to understand why that's happening, and if it's happening, it could be a problem. You want to evaluate it and have high confidence in that assessment. Enduring changes, deviations, and waivers, all that is very important to check and make sure you have a good handle of that. Lesson learned in certifying space structure. You want to understand the baseline design margins before you assess a non-conformance. If you don't have a good understanding of baseline design margins, then assessing the non-conforming condition, it also becomes less clear. So analysis techniques, material strength, and failure mode should be carefully validated and well understood for the baseline design. Hardware discrepancy can then be assessed relative to the baseline design. You want to make sure that you build the confidence through the building block approach and analysis. And now I can use the analysis to check the hardware discrepancies. Now, issues with the baseline design have led to costly redesign late in production. So later on, when you have an issue later on and you find, whoa, my analysis is not good, uh, it could call a whole design in question. You also want to implement clear acceptance drawing requirements. It's possible that the requirements in the drawings are not very clear, so operators and technicians will apply the drawings incorrectly, and even the engineering team will be applying incorrectly. So, say you have a flaw criteria that's not clear, that could be a problem because people could interpret that criteria, like spacing between flaws, for example, that could be interpreted incorrectly. And so that could lead to a costly reassessment of the whole stockpile that you have. And that has happened both on aircraft and launch vehicles. You also want to ensure that the build paperwork is clear. The build paperwork gives instructions to the manufacturer on how everything is put together. It's basically how you implement the drawing into into what you're doing. And so it's very important that you do have a clear understanding of that, because if you don't have the build paperwork correctly assessed, um, if the bill paperwork is not clear, then there could be an issue. And as an example, the ply angle was incorrect in the bill paperwork, and as a consequence, the hardware was designed with a wrong ply angle. Therefore, that led to a costly failure later, which led to costly redesigns. So that's an example of making sure having a bill paperwork pays off. But this is not just the only example, there's many of them. Process changes at the supplier level could be a problem and should be monitored and evaluated. Process changes at the supplier level led to metallurgy, which led to sizable strength reduction, which led to a redesign late in production. So it's important that any changes at the supplier level, you know what's going on, because that can impact the qualification that you had already done. And in this case, metallurgy issues was the issue here. You want to ensure the materials requirements are sufficient for the parts intended use. You had a structure here that passed a proof test and then failed right after another proof test. That shouldn't have happened, but then you look at fracture surfaces and there's correction products in it, which were caused by moisture intrusion. Well, guess what? The material spec did not require tests for this particular failure mode. And so missing that was the real issue. Not that there was corrosion products, but that the material spec was not good enough for what you needed, for what the part needed. You also want to ensure that whatever the drawing, sometimes you have drawings that have tolerances, and you may ask where they came from. Sometimes they're based on experience. But you want to make sure that the drawing tolerances are not such that when you're at the, because remember the analysis is done with nominal drawing tolerances. But if now your drawing tolerances allows for uh, more variations, you know, the tolerances in the drawings could be a problem. So say the thickness is allowed to go down to 10 mils. Well, you want to make sure your analysis can survive that. And sometimes it's actually a good idea to analyze to the minimum maximum tolerances to make sure you're not missing something. Buckling evaluations are very sensitive to tolerances, and so therefore drawing tolerances should be evaluated and should be tied to some sort of measurement technique. The majority of risk of failure is retired after workmanship. So, and why is that? It truncates dispersions. You truncate the modeling uncertainty, the strength variability, material variability, and build to build variability. The modeling uncertainty gets truncated only if you have an analysis that has been validated. If it's not, and if the proof testing that you're doing is comprehensive. If it's not, then it's not fully doing that. But there is benefit. Once you pass a proof test, you're fairly in good shape. And as a consequence, if you want to do an acceptance test program that's comprehensive, you want to make sure it's good. And so if you change anything after the acceptance test, or you change anything after the post qualification testing, that can be a problem. And you want to make sure that any changes to the post qualification be evaluated. Proof test failures have occurred because people thought that they were improving their hardware, but instead it was detrimental to the hardware. Evaluating proof test anomalies is quite important. You want to pay attention closely to audible noises, nonlinear responses in the behavior, because you're going to have strain gauges during the proof test. And you may feel very tempted to say, I don't think these are issues. But in a lot of these instances, in some instances, must say, post proof NDI discovered damage growth. And so it's very important to understand that NDI is going to provide a lot of value. So if you can do it, do it. Because if you don't do it, and any of these anomalies in the proof test occurred and it had to do with damage, it can subsequently lead to a flight issue. So again, any proof test anomalies should be evaluated carefully. I'm not saying always implement NDI, but for the most part, you want to make sure you have a good understanding of what went on. Proof tests at operating environments, very important. Some materials exhibit higher strength at operating temperatures, but a degradation in fracture toughness. So when you're correcting the proof test to account for the difference between flight and the ground, because when you do a test on the ground, you may not test at the correct operating environments. It's important to understand the driving failure mode. If the driving failure mode is fracture toughness, then you should adjust the test on the ground based on the fracture toughness differences between the flight conditions and the ground conditions. But if strength is a driving failure mode, then you want to adjust the proof test based on strength differences between flight conditions and ground conditions. So whatever the failure mode is, that's how you want to size that proof test and come up with what I need to do to overcome the test likely flight differences. And so that right here concludes the launch vehicle designs, how we go about it philosophically, how we go about it with equations, how we go about it in the sense of bringing all the pieces together. In summary, what we covered is a comprehensive approach to spacecraft design, launch vehicle design. We didn't go through all the equations as covered in portion two, a lot of that, but I do want to pay attention, point to kind of the processes, right? It starts early in the process. It starts understanding. It starts really understanding the the mission objectives that you have in mind. It comes down to understanding the loading environments that the launch vehicle is going to experience, and that's going to take into account the mission objectives, the masses, it's going to involve all the different disciplines, guidance and control, the fluid mechanics. That you want to make sure that the launch vehicle design, you get the loads validated through wind tunnel testing and scale that up, and then really understand the dynamics. The dynamics then drives the structural loads, which are then verified through component level testing and also analyzed further to make sure you're protected against the A basis and the 9990 loads. So this concludes this particular lecture. We're going to now move on to aircraft design.